Finally, minimize, start the PowerPoint, and we are off. Okay. So, as I stated and as I made lists earlier on, there are many different ways in which we can find the delta H. Some of them are experimental. I guess in grade 11 I would have said empirical, right? We can measure it in the laboratory. We can measure temperatures, et cetera, right? So like number 2 was calorimetry, right? Calorimetry. And number 1, right, was the molar enthalpies. And that was the delta H equals N delta HX. And calorimetry was when we brought in the Q, negative MC delta T equals N delta HX, right? So we can calculate all these things that's equal to delta H. So I can get delta H if I know the molar enthalpies. That would be maybe found on a table or in that big book. That's probably empirical. Some, chemists did a lot of work to calculate what those molar enthalpies are, so they likely calculated that and put it in a table for us to use. How nice that was. And this one is in the lab. When we did the experiment, we measured some T's, and we could get that. And now we want to talk about some theoretical methods. And number 3, bond energies, right? And this is a theoretical, this is an idea, this is a theory that we use to get these. So this is more of an estimation. And then we're going to do Hess's law, that's coming up. And that's also kind of a theoretical, actually it can be a mixture of both. And then 5, we're going to do the heats of formation. And again, those last ones are kind of mathematical tricks we use using existing data. So is it really theoretical? It could be experimental, but bond energies is truly an idea. We assume that the energy, the potential energy, that EP, is stored in the bonds themselves. And if we mathematically add up how many bonds we have to break and how many bonds we have to make, we should be able to figure out what the delta H is. And that's what this lesson is about. So let's talk about what happens during a chemical reaction in terms of their bonds on a bond-by-bond basis. And here I'm using a simple representation of the decomposition of water molecules into their constituent elements, hydrogen and oxygen. This is the reaction that takes place in the Huffman apparatus. If you think back to grade 9, you remember that apparatus, lots of glass tubes kind of stuck together. Your teacher would have plugged in some electrodes, inputted some electrical energy, and that then separated the hydrogen from the oxygen, and you would have done a gas test to prove their identities. And so in this context, and I've also included some simple structural diagrams, I guess just as a reminder to, in preparation for our test next week, these don't have lone pairs on them, and therefore they're not Lewis diagrams. Lewis diagrams would contain the dots for the lone pairs, so we call these just structural diagrams because we're just interested in the bond connections. We're going to have to draw some of these simple ones in this lesson. If you do include the lone pairs, it doesn't change the analysis of the problem. Because if I were to put lone pairs on here like this, all right, and like this, it doesn't change which bonds are being broken, all right? So in our analysis, when we have reactants, we have to break the bonds. We're imagining as if we're taking apart a bunch of models. We're separating out the individual atoms. Energy is needed to break bonds. If you think of the chemical bonds as being little springs and the fact that they're being held together, you'd have to expend some energy to pull those atoms apart, and therefore you'd have to put some energy in to do that. I don't have my little magnets with me as I normally do. These aren't bad. They're pretty wimpy, but they're not bad. Just like if you have two magnets held together by some force of attraction, if I want to pull these apart and make them individuals, then I'm going to have to do some work in order to expend some energy to do that. I have to input some energy to break a bond, okay? So bond breaking is endothermic. You put energy in. So we can calculate a delta H for, well, we can estimate a delta H for the individual bonds being broken. That energy has to go into it. On the other side, when we rearrange the product atoms, when the products are coming together, we imagine that we bring those atoms together to form their little molecules. And again, I don't have to push them together. They come together all on their own. In this case, when I let the magnets snap together, you can hear some sound energy go off into the room. That's an energy giving off process. And the same thing is true when the atoms snap together. They vibrate as they do that, and that gives off heat energy as they come in and form their bonds. So making bonds is an exothermic process, all right? And therefore, its delta H is negative. It's giving off that heat energy to the surroundings, okay? All right. So there is the essence of it. So let's now define bond energy. Now, in a moment, I'm going to put up a slide that has a table of bond energies. And this is one of the tables that is found in the reference materials. So if you've already printed out that page, you don't need to take this sheet. You can just open it up and look at it. This is my copy with a nice plastic protectory thing. This is the one that I use for tests. But I'll hand it out so that you can look at it today. When you're finished, we'll just gather them back in for today. Do you want one of these? Even if you've got it printed out, I can give you one, because then you don't have to go digging for it or finding it, right? Everybody need one in this row probably, right? 1, 2, 3, 4. You can see on this table that there are many other tables. You'll notice some have some other lettering on it and some other values. But you're looking for the one that says average bond energy. 1, 2, 3, 4. There you go. 1 and 2. There you go. So what is the bond energy? It's the amount of energy required to break 1 mole of bonds between 2 particular atoms. And not only is it between the atoms, but it is the type of bond that it has. So a single bond between 2 carbons would have a different bond energy than a double bond, all right? Double bonds are stronger than single bonds. We're going to find it takes more energy to break and make those bonds. The amount of energy released when 1 mole of bonds is formed. So again, we're working on a per mole basis. So again, we will be dealing with kilojoules. We're good to go? Good to go? Good to go? Just because I'm recording, it doesn't actually see you, Cammie Sinclair. That's what she was going for. All right. So here you can see our table of bond energies. And the textbook, the questions that I assign, will guide you to a table in the appendix. But I'm going to use this table. So when you're answering the questions out of the textbook, you can use this table, but your answers might be a little bit different, all right? Because bond energies are truly averages. I'll talk about that in a moment. So if you use this table when you do your practice problems, you might find they're different than the actual answers. We're going for closeness then, all right? If you use the table out of the book, it should be closer because that's the table. But I like this because I don't want you to have to open your book when doing a test. I need you to have the bond energies in front of you. What did I do? I did a Google search for bond energies until I found a nice one that was nice, easy to transfer, and I went with this. So let's take a look closely at what this states. So you'll notice here that we've just got kind of a list, and it seems to be in terms of elements. Here's hydrogen bonding with various other atoms. Here's carbon bonding with various other atoms. Notice all single bonds. Nitrogen bonding with various atoms, oxygen bonding with various atoms, fluorine, chlorine, iodine, some sulfur, and some silicon. Obviously, it's not all. Obviously, it's a lot of non-metals because we're talking about bonding molecules, right? We're not talking about ionic compounds. And then here we have some important multiple bonds. Some things to notice. Notice that there's no signs on these numbers, and that's because it depends on whether we're breaking or making the bonds, right? Remember, it's endothermic if you're breaking them, which means they'll have a positive sign, and it's exothermic if you're forming the bonds in the products. That'll give it a negative sign, okay? If we make some interesting comparisons here, if we take a look at carbon bonding with carbon, carbon single bond carbon, 347 kilojoules per mole, and then if we jump to the double bond, notice 614 kilojoules per mole. Not quite double. You might expect it to be because it's a double bond, but it's not as simple as just doubling the connection, right? So it is higher though. Notice again, the triple bond now 839 kilojoules per mole. So lots of energy is stored in those multiple bonds, okay? Another interesting thing to look at is the nitrogen triple bond nitrogen. It is the strongest bond, all right? I don't know if there's any other stronger bond than nitrogen triple bond nitrogen. It's one of the stronger bonds in nature, and I would have told you that last year when we did the explosion of the nitrogen triiodide. Remember the purple stuff over there, and I hit it and went bang, you know, that type of thing. And that's because those nitrogen atoms desperately want to snap back together to release that 941 kilojoules of energy per mole. That's what makes it so explosive. All right, one thing to note, and I don't like the way it's written here. I've got an extra little double in here to represent double bond. Notice it says here, the C double bond O in CO2 is worth 799 kilojoules per mole for each double bond. But if we just go to the CO bond, notice 745. What does this indicate? It indicates in CO2 that the bonds are a little bit stronger, the C double bond O. Now this illustrates something very important. Bond energies, like I said, are really an estimation. We've, as chemists, looked at many examples of these bonds, and we've averaged their bond energies that we've attempted to calculate. Every bond in every individual molecule has a slightly different bond energy than a similar bond in a different molecule. The neighboring atoms themselves can affect the way they form the bonds. So a C double bond O in carbon dioxide has a different strength than a C double bond O in another molecule. I'm not going to try to name another one. We haven't done enough of that yet. But these are just averages of many examples of bonds that have been sampled over many different compounds, which makes this really an estimating tool. Let's say you planned on testing a reaction in the laboratory, and it's one that maybe no one has ever done before, so you want to estimate what the delta H is going to be that you might get for these molecules. You could use this calculation to get an estimation to see if you're in the right ballpark. But it's not a perfect calculation. Well, it is a perfect calculation. It's not an actual perfect number because they're all estimated values. Okie dokie, let's continue. So how do we then calculate the delta H for a particular reaction? Now, in the past, when I've taught this, students used to know very well what that symbol was in front of the reactant bond energies, and that's because it used to be part of the math curriculum. But as the math curriculum changes, you guys encounter this term or this picture at various times. This particular symbol right there, all right, is a Greek letter, and it is a capital sigma. Typically, it's got little legs on it as well, right? It's a capital sigma, which is really, in essence, a capital S in regular alphabet. The lowercase sigma looks like this, and we're going to use it later on. So it's a capital sigma, and I don't know, have you encountered that before, sigma? What does it mean? The sum of. Awesome. So this simply means the sum of. It means you're adding it together. See, and again, 2 people knew it, and the rest of you haven't encountered that yet. So I don't know where it ends up in the math anymore. Yeah. What course do you take it in? Data management. So if you haven't taken data, then you don't know it. It simply means we're going to sum up all of those things. Now, at this point, I've never really done another step to the equation because I've just added them all up at this point. I just did a total of it. But I'm going to make reference to the textbook because you might want to go to the textbook to make reference. And so what they do there is they have it written down as the sum of, all right, and then n, which represents the number of those bonds. I guess it's the number of moles of, but the number of, that's fine. And then they multiply it by, and they use the symbol D, all right? And the D represents the bond energies. In this case, it's the D of the, and I'm going to put here a subscript, bonds broke, all right? So it's N times the bond energy for the bonds that are broke, all right? So it's the sum of those. We have to total all those up, minus, and then again, the sum of N times the D's for the bonds formed. All right, and the only reason, oops, we'll make that a big bracket there. The only reason I'm writing that is because, well, number one, for the video, I'd like it to be a little more systematic for people who are watching it. And number two, it's in line with our textbook. Okay? Now, let's just analyze this equation for a moment before we use it. Remember, bonds breaking is endothermic. And notice, you might think it's a subtraction, but really, this is an addition of 2 H's for the bonds. Because this is endothermic, this first term, endothermic means positive, right? So this is actually the positive value for the bonds broken, because when you break bonds, you put energy in. So we use the positive version of the number in the table. And then what we're really doing is we're adding the energy of the bonds formed. But because bonds formed are exothermic, their sign will be negative. And so this negative sign actually means we have energy given off when we form bonds. So really, we're simply totaling up the energy for bonds broken and the bonds formed, but because bonds formed is exothermic, it has a negative in front of it, okay? So that negative actually comes from the fact that when you form bonds, it's an exothermic process. So it looks like a difference, it looks like we're doing a subtraction, but we're really adding the amount of energy we input to break the bonds, and then we're adding the amount of energy we get back out to make the bonds, and then it's really like a bank account. Did we end up putting more energy in to break the bonds, or did we end up getting more energy out when we made the bonds? That's what's going to determine the delta H. Okay, let's do some examples. So here's our reaction. This time I flipped it around. We are forming water molecules from its elements. And as I stated, in preparation for your test, I've added on that you need to be able to do the Lewis diagrams for the nice ones. And the reason I put that is because you need to be able to draw the simple structures for these elements and molecules in order to total up their bonds. So you need to be able to draw them properly. Like I said, I'm not going to give you any ugly ones, so I don't need you to be able to do that even on the review test. So number one, we have to balance our chemical equation. That is not balanced. So what am I doing here to balance this? This is just to make you squirm a little bit. We're balancing H2 plus O2 to make H2O. You're all staring at me like, what the? It's awesome. Yep. So 2 of these to make 2 of those. Nice. It was just on the picture 2 slides back. That's okay. And now we need to draw the molecules because we need to see the bonds. So in order to do bond energy calculations, you need to be able to draw them. If they're simple ones, I expect you to be able to do them. If I'm asking you a question that has a complex molecule in it, I will supply you with the diagram of it. So H2 is H and H. And you know what? You can put a 2 in front of there if you'd like. That means you've got to realize that you've got 2 of these bonds. But you know what? If you draw it right out, you can see that you've got to break 2 of those bonds in order to make the water. 1 oxygen molecule. Remember, oxygen has a double bond. It's got 2 lone electrons that are going to want to do a little overlap there. And there's only 1 of those. And then I've got 2 water molecules, and I'm really hoping that we are okay with this maneuver here. Again, lone pairs are not needed for these diagrams. I guess on the grade 11 review test, if I ask you to draw the Lewis diagram of, Lewis diagrams do have lone pairs. So this is why the textbook likes to do this. What I normally would do would just dive in and start writing numbers down. But if I'm going to do it like the textbook, the delta H is going to be equal to, and now I have to add up all of these bonds. You'll notice I have 2. That's the N. Oh, actually, you know what? Hold on. I want to get rid of that. No, I want to get rid of that. Is equal to N, all right? And then that is times DHH. And actually, it needs a subscript, NHH DHH. The number of HH bonds versus the energy of the HH bonds. And you know what? If you find you don't need to write this step down and you can just start writing down the numbers, that's awesome. But I'm just including it because it shows the steps that they do in the textbook, okay? Plus the N of the O bonds times the D of the O bonds. And that's all of the reactants, so we put that in brackets. Minus. There are only OH bonds. There's 4 of them. We'll put that in a moment. The number of OH bonds, or HO, it doesn't matter. So I'm now counting OH bonds, times the D, which is the bond energy of the OH bonds. And that's it on that side. Now let's put the numbers in, because we're doing it step by step. In this case, now I've got 2 of those times, and could somebody please find me the HH value on the sheet? Yep. 432? 432 kilojoules per mole, but don't write that in. That's a pain. Right? If this is kilojoules per mole, the 2 represents 2 moles. They cancel out. You're going to get kilojoules in the end. Plus 1. What's the energy of a O double bond O? Sorry? 495. 495 minus. And notice there's 1, 2, 3, 4. There's 4 OH bonds. There's only 2 molecules, but each molecule has 2 bonds in it. And what is our OH? bond energy. Yep. 467. 467 kilojoules per mole. Personally, myself, I've made mistakes doing calculations like this a million times. And that's because you've got brackets upon brackets and you get the negative in the wrong spot. Personally, myself, I like to get a number on the one side, get a number on the other side. Then I can see if I'm in the right ballpark and get an answer. All right? On a test, right, if you write all this in and then you get that wrong, I actually could give you part marks here if you get these right. You see what I mean? Or you get this one right and that one wrong, I can say, oh, you screwed up something over here, part marks. So I like to see that intermediate step. Could somebody give me the numbers that they got for those intermediate steps? You got some numbers? Calculator's out of batteries. Is it because solar and you're in the dark? Yeah, you were in a bad spot for solar calculator power, yes. I'll take the numbers when you get them. No one wants to share? No? What do you got there?
1,359.
First one?
Yeah.
1,359. Okay. 1,868, which means if we think about it, we got more energy out from putting the bonds together than we had to put in. Okay? And what did you get when you subtracted them?
Negative
3,000. 227? 227 kilojoules, and it's a delta H, so it's not kilojoules per mole, it's the kilojoules for that reaction. We don't like those numbers. What don't we like? Oh yeah, what did you do? You must have added those together. This should be this minus this. We won't tell the world that Mitch made that mistake. What did we get? Negative, did you say 509? 509 kilojoules, not per mole, because it's just a delta H for that entire reaction, right? I guess it's per mole of oxygen because it's got a 1, right? Remember, that was yesterday's lesson. So we just leave it as kilojoules. Okay? Exothermic. Makes sense? When you burn hydrogen and oxygen, you get a lot of energy out of it. All right? Okay. The question was, is this a long note? This is my last example, and then I will give you some work, and you can work away. I would expect you to be able to draw the structures for all of those. That's not, there's no ugly ones in there. Again, on a test, if I'm asking you to do something that I feel is complex, I will supply you with the structure. Balancing is the best thing to do first, because then you can start drawing. 0.5s aren't going to be very good here, because you have to draw out entire molecules, and to draw out a half one, it becomes an issue. So you'd want to get rid of any 0.5s. So what do we got? 1, 1, 4, 2, and that gives me 1, 2. Is it just 2 oxygen? Did I do that right? Yeah, I'm losing it. And I can't erase. No, wait a minute. 4, 2 is good. 1, 2, 3, 4, 2. 2. 202. I'm questioning myself because I can't erase. My erase feature doesn't work, so I just scribble. And that's not professional for YouTube. YouTube does not allow unprofessional stuff on it, I hear. Only classy stuff on YouTube. I don't watch a lot of YouTube, as you can tell. CH4, I'm hoping that you ultimately would come up with something like this. Carbon has 4 bonds, hydrogen gets 1. O2, you got a couple of those. CO2, do we remember CO2? What kind of bonds are coming off of that C? Yep, 2 double bonds. and then 2 waters again. And you know what? If you are comfortable not necessarily having to draw out the multiple ones and just putting a 2 there and then realizing you need 2 of those O double bonds, that's awesome. If you draw it out like that, it's visual right in front of you. Again, because I want it to look like the textbook, you know what? Many of you could probably go straight to the question. 4 of those plus 2 of those, right? Pulling the numbers out. That's okay. I don't need to see this middle step, but I'm going to put it. Delta H is going to be the number of CH bonds times the CH bond energy plus the number of O double bond O times the bond energy for O double bond O minus the number of C double bond O. Be careful. This is the CO bond in a carbon dioxide molecule, which means you need to use the bigger number at the bottom of the page if you're working ahead of me, right? Times the bond energy for C double bond O for carbon dioxide. And then we've got NOH times the D for OH. And now we can get some numbers. There's 4 of these. And I will come back and get this information from you because you're working away. And there's 2 of those. And we've got 2 of those. And we've got 4 of those. And you're working away, so I will look some up myself. CH, 413. That looks like that's 413. O2, we've already seen that guy. O2 is 495. 495, some pretty strong bonds in there. CO, and that's the guy at the bottom, 799. 799. And we've done OH, 467. 467. 467. Again, I have personally made a mistake in that step. I don't know how many times. University, get my stuff back. Oh, that was so stupid. Where I stick a negative in the wrong spot or something because I'm trying to use the calculator all in one shot. So what do we have for each of these? What's the total energy of the bonds broken? Got a number there, Lily? You're waiting? No, you're just hanging out? Waiting? All right. Mitch is brave. Mitch makes a mistake. He's still going to give me numbers. What do you got, Mitch? 2,642. And? 3,400. And now he's going to atone for his mathematical blunder on the last one, and he's going to tell me it is? 24 kilojoules. Again, exothermic, we're talking about combustion of methane gas. That's going to give lots of energy off. So if we then actually did an experiment, we would hope we would get close to this. But again, remember, bond energies are averages of many bonds over many molecules that chemists have done the math on. And therefore, it really only gives us an estimation of the delta H. But still, sometimes it's nice to get an estimation if there's a molecule that you've never dealt with before. All right. Homework. Okay. And that's that.